तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we were looking at how to deal with incompressibility. In that process, we saw that one of the things that we can do is to do a selective reduced integration. One of the techniques what we saw was to modify D, but the other technique which we saw was to modify B. So one of the comments at the end of the class which is very important is the way we write B. How do we write B? Because this also depends upon two things. One is the order in which you write epsilon. Whether you write it as epsilon 1 1, 2 2, 3 3, 1 2, 2 3, 3 1, or in some other order 1 1, 2 2, 3 3, 3 1, or whatever it is. So depending upon that, B will change. That's very fundamental. Maybe all of you know it. Please take care of that. The next one, what also is important, is the order in which you write U. You can write U in different orders. So for example, you can write this as U1 V1, U2 V2, and so on, and call them as U1 U2 U3 U4 U5 U6 U7 U8. Okay, for say a 4 noded element. Of course, already you know that the size of this depends upon 2D or 3D. These are issues which I just want to bring it to your notice. Or you can even change this order. You can say U1 U2 U3 U4, then V1 V2 V3 V4. Okay, you should be consistent in writing it when you implement it. So that will settle. That's why there you might have felt that there's a difference in the way I wrote B. Okay, so that's very obvious. As long as you know that B is that S into N into U, and as long as you know this is what goes in, you can adjust B. That's not an issue. The second thing is that we said that this KT can be decomposed into two parts. One is what we called as B dilatational plus deviatoric transpose, say dt, B dilatational plus B deviatoric. So there was a question that there can be cross terms. Of course, there are going to be cross terms. So there are various ways in which people have implemented this. In order to look at it very cleanly as a selective reduced integration, we don't take into account the cross terms. The question was, am I correct in doing it? Yeah, you are not correct. Okay, if you remove the cross terms, you're not correct in doing it. But what people have done over the years is to adopt their own procedure, okay, so that their results are met in the sense that the incompressibility condition is satisfied. So in other words, what we call as B bar method has taken different shapes, no doubt about that. Okay, so in one of the implementation, people feel that they can write this P as B transpose, say sigma, okay, into d omega, and say that sigma can be split into deviatoric and the dilatational part, and use only B dilatational separately and B deviatoric separately. In fact, many of the flow formulations in plasticity, which is used for doing metal forming problems, okay, they use this in a very simple fashion. They will not look at the cross terms, they will take B dilatational dt, B dilatational deviatoric separately, and then they add this together. Okay, they get the result, it works, right? But strictly speaking, you are not very correct in doing it. Okay, that answers your question. So you can't just like that neglect it. There are other ways in which people have done it. What are the other ways in which people have done it? The implementations, there are so many implementations. The other way is to calculate B at a reduced Gauss point and call this as B bar. So instead of evaluating it at, say, 4 Gauss points, which you do for this, you evaluate B dilatational at, say, 1 Gauss point. Okay, this is the standard procedure of Hughes. So this and this part, okay, both of them are evaluated at, say, a single Gauss point. Many people together they call this as B bar method. So B bar transpose dt B bar and so on. Okay, the essence of the story is that the B term is split into 2 parts. Okay, and that the culprit dilatational part is the one where maximum emphasis or maximum attention is given. This is what I explained in the initially when I said that there are 2 parts to K matrix itself. Okay, when I look at it from D, aspects of D, and that one fellow who's the culprit who's going to make that infinity is a guy who's going to make, when nu is equal to say 0.5, make the one of the terms to be infinity. But having said this, then there may be a doubt, is it an ad hoc procedure? Is it that ad hoc procedure came out of some sort of a justification from what I gave in the last class, or does it have any variational basis to the whole thing? After all, finite element may be looked at as an ad hoc procedure, okay, especially when you look at finite element from the perspective of the development, early development in the 50s. Okay, but it's actually not ad hoc. It has a very sound mathematical basis. So same question you can ask here, does it have any variational basis which forms the foundation stones of finite element analysis? The variational basis for this comes from what is called as mixed formulation. We are going to see how, when I develop mixed formulation, now how closely we are to this kind of formulation. Now what is mixed formulation? Mixed formulation ultimately leads to a variational form based on what is called as Hu-Washisu, Chinese and Japanese scholars who came together or who simultaneously proposed Hu-Washisu variational forms. In fact, there's a very interesting book by Washisu. If you have access to it, please look at that. Variational methods in elasticity and plasticity. But let us now concentrate on this. All our formulations so far are based on displacements. Now, the current formulations what we are going to use are not only based on displacements, but also are based on stress, okay, either stress or pressure, sigma or P, as well as the volumetric strains, okay, which is denoted by epsilon V or theta in different ways. It can be either P or sigma, this or this, and epsilon V, or people can use also what is called as J. We will come to what is this J, okay, in a finite deformation case later. Now what is this mixed formulation? When we go to U, we go to what is called as an irreducible form. You can't go below U. Simply talking, you can't go below U. U is the variable to which you can go down. When you are in sigma, it is not, we are not talking about an irreducible form. It's a reducible form. From sigma I can go to strain. From strain I can go to U. right? So it is not an irreducible form. So U is one where it is irreducible, okay, and straight displacement formulation. In mixed formulation, we have forms which are both reducible and irreducible. But interestingly, we will remove the dependence of these later. Okay, you will see that we will remove those dependence, but simply means that you have three things. You will, in other words, you are going to treat them as if they are also, these two guys here, as if they are also variables like U. Is that clear? Okay. Now, having said that, let us develop this theory and see on mixed formulation. It's not very difficult, it's quite simple. Implementation may be slightly difficult, but the theory is not very difficult. So we follow Taylor and Zienkiewicz as we develop this mixed formulation. Okay. Yeah, I think one comment is in order. There are other types of formulations as well, and probably one of the comments which was passed in the in my earlier course is that the strains have to be enhanced in order to meet certain demands, say for example while bending. Okay. So an ordinary element, a quadrilateral element, cannot take bending, okay, and hence you have what are called as enhanced strains to take care of that, so that it can bend. You can have though you have 4 degrees of freedom, it can still take the shape as it bends. So in other words, an element which is like this in bending, or rather, sorry, it takes like that shape when bending. It's not a nice shape which you would like to get, but you would like to get a shape which is like that, and so on. So that kind of shape are possible by enhancing the formulation or enhancing the strain calculation. Epsilon is not only now a function of U of my original finite element, but also is enhanced such that I can handle such situation. So epsilon consists of 2 terms, the regular epsilon term, say let us say R plus enhanced terms. So this formulation is different from mixed formulation. So you have also combination of these two as enhanced mixed formulation or mixed enhanced formulation. So you have different combinations as well. Is that clear? Okay. So now let us start our procedure. So let us start with the definition of what is called as YUM. So let me define YUM to be 1 1 1 0 0 0. So this is standard way in which Zienkiewicz and Taylor define ultimately the equations in terms of the matrix forms. Okay. In fact, just to illustrate that it's a matrix form, it's important that we write this down, so that ID matrix is defined as I minus 1/3 of M transpose. This is very helpful to us to split the deviatoric part, and the dilatational part. That's I is split into deviatoric and dilatational part. So that's very useful. So we define an ID matrix, okay, as I minus 1/3 T. Remember that we already said that epsilon is equal to SU, right, and sigma consists of 2 things. We will see what it is in a minute, but we can as well write that, okay, in terms of 2 parts here before we go to sigma, dilatational deviatoric part, and write epsilon to consist of id into su, first part of it, plus 1/3 m epsilon v. That is the dilatational and the deviatoric part of epsilon. You can tell me, look at this, what would be the dilatational part? Yeah, 1/3 m epsilon v. Yeah, that's the two parts. We are splitting that into two parts and writing that. M is, what is m? M is this. It is, I mean, it is just as I told you, don't put a physical meaning to m. It is just a way of writing so that you can write the whole formulation in a matrix notation. There's no physical meaning to m. It's just like unit matrix. Okay, you have 1 1 1 0 0 0 1 and so on, right? So this is a way of writing the indical notations or the tensorial notations into a, writing them into a form which is more amenable for implementation. That's all, right? Or else it becomes difficult to implement. Now let us look at sigma term. Sigma can be split again as id sigma. Okay, I'm using this sigma with a v on top. Okay, because I'm going to, please note all of them are matrices. I'm not going to, you know the situation and you can write it. I'm not going to every time put that as a matrix. Maybe we can look at this as an underscore. In a board, when you write, you want to put all the matrix form, it becomes a bit complex. So sigma is again split into two categories, that plus m into p. Epsilon v, of course, you know, is ii plus jj plus kk. Sorry, 1 1 2 2 plus 3 3, or epsilon ii. So again, sigma is split into two terms, the deviatoric term and the dilatational term. This sigma here is the guy who participates in the constitutive equation, and depending upon the way you write the constitutive equation, it can be written as, say, delta sigma is some function of delta epsilon. Remember, this we derived in the last class, the relationship between delta sigma and delta epsilon as dt. Okay, but why we have written it like that is because this formulation, what we are going to develop, is not only applicable for our small strain plasticity, which we are dealing with now, but are also applicable for a variety of other situations where incompressibility is an issue. Any other constitutive equation, incompressibility is an issue, you can use this. But we are still in the small strain regime, so you cannot use this formulation for large deformation. You have to make some amends if you want to use this for large deformation. Right? Is that clear? Okay, having said that, let us look at the variational or rather the Galerkin formulation of this. I'm not going to write the Hugh-Vasilichev principle. Maybe we'll go into details later. Now let me look at the second step, and I'll explain what this means, the step means. Just to okay, memory, we said that you can write down in the last course, we said that we can write down a variational form, and then we can write down the minimization of the variational principle, which we wrote it as delta I, and said that the variational of this, or the minimization of this variational principle, leads to virtual work principle, right? So you can either go to virtual work or to variational form, and we also made a comment that many times variational form may not be available, so you stop with the virtual work principle, okay, because you need a constitutive equation if you have to go to the next step. and especially in a situation like plasticity, you may not be correct to go to a variational form straight away and write it, may not be very mathematically very correct, okay, because you don't have a strain energy function. Most of the variational forms are written in terms of strain energies, and you do not have strain energies relationship like what you have for elasticity, so you may not be very correct. But the next step where we write down the Galerkin form or virtual work form is fine for many of these things. So let me write down the virtual work form for this. Now what I am going to write down also involves the inertia part of the force, okay. So if you want to include it, you can include it, or you can neglect it as well. So the first term is that inertial force rho u double dot d omega, that's the first term, plus delta of S u transpose. Note what is delta S u transpose is actually delta epsilon transpose, nothing else, sigma d omega, okay. These are the two terms which are, happens to be available for us as internal forces, is equal to the external virtual work, which happens to be delta u transpose b d omega plus delta u transpose t theta or d gamma. No, these are see, the internal virtual work is equal to the external virtual work, our underlying principle. Last time we did that. So these two, left hand side and the right hand side, are the same. But the main difference is that we do not stop with this. We write down two more equations for P as well as for the volumetric strains. So let us write down the second equation for volumetric strain. So that is written as delta epsilon v, maybe integral delta epsilon v. Note this term carefully and let me have your comments. Into 1/3 m transpose minus p, okay, d omega is equal to 0. And next term, let me write down the next term. Watch this carefully and tell me your comment. Delta p into m transpose SU minus epsilon v d omega is equal to 0. Look at those two terms. Can you pass some comments? Delta epsilon v. Epsilon v is the volumetric strain, okay, and delta p is the variation in pressure. We said that we are going to have three things, like we had delta u in the first case, here we had delta u in the first case. We should also have variation in p as well as in epsilon v. So those two also enter into picture. Delta u is a virtual displacement. Delta epsilon v. Delta epsilon v is the variation in the volumetric strain. Delta p is the variation in the pressure, right? Please note one thing carefully. I mean, again I am commenting, we did that in the last class because it's good to remember these things. In delta u, you call this as virtual displacement. Now, you may wonder what is this virtual displacement. So it is just that mathematically you may understand this equation, but as engineers many times you are more comfortable to look at terms like displacement, force, pressure, energy and so on. So just to give you a physical flavor to the whole mathematics, we call this as virtual displacement, we call this left hand side as internal virtual work and call that right hand side as external virtual work and so on. In actuality, if you look at it, there is no need for you to call delta U to be a virtual displacement. You can just leave it as it is. If you want, even you can call it as a virtual temperature. It does not matter. As long as you understand that it's a variation of U. So variational calculus does not depend upon you calling this as virtual displacement. Right. So let us now concentrate on these two equations. Can you comment on this, how we got this two equations? Very, very simple, straightforward, as we did. If you want to go back and look at the formulation which we did for our variational formulation which we did for this, how we started from equilibrium equation and came here, you see it. Can you comment on it? Weighted residual of the equation, but how did I put it as, you're absolutely right, it's a weighted residual, but how did I put it as 0? What did I do? Look at that slightly more carefully.
Quantity inside the bracket must be satisfied at all.
Absolutely, quantity inside the bracket should be satisfied at all points, and this has to be equal to 0. Okay, actually what is that we did? P is equal to nothing but 1/3 of sigma. So this is nothing but 0 multiplied by some quantity. This is exactly what we did, if you remember, on our variational form itself. When we got the variational form, this is what we said we can play either from equilibrium equation, you can go to the variational form, from variational form, okay, Euler-Lagrange equation, I can come back and so on. In one side, one route when I took, what I did was exactly the same. Anything multiplied by 0 is equal to 0. Okay, so it has to be satisfied at all points, and in other words, when I discretize it, as our friend here said, that it is a weighted, okay, residual of this quantity. Look at that. Here again, this is epsilon v, of course, I hope you know. Here again, it's exactly the same. 1/3 here and m transpose epsilon, which happens to be epsilon v. So this quantity has to be 0, that multiplied by variational form of delta p. Okay, so these are the three equations which we now use in order to develop the finite element solution. Is there any questions? So you can combine them together and write also a Hughes-Issue variation principle, but I'll defer that till we develop finite strain plasticity, finite strain elasticity and plasticity. And at that time we will write this down, because now it is very easy to understand, okay, at this stage, right? But maybe I will leave it as an exercise in the same fashion as we did in the first course when we converted this variational form into a functional. You can try to convert this into a functional form. So it's very simple. Okay, so Hughes issue, though it's a brilliant idea, has come from very, very simple concept, nothing very difficult to understand. Now, what's the next step? What I'm going to do? Now I'm going to do exactly what I did for n, for u, for p, as well as for epsilon v. So in other words, I'm going to write u is equal to my good old friend shape function into, say, u hat. Okay, what is u hat? Remember, yesterday we said that they are the displacement of the nodes. Right. I'm going to do the same thing for pressure. I'm going to say that P is equal to n p hat, and I'm going to do that for epsilon v. So epsilon v is equal to n, sorry, let me do that a minute later, epsilon p hat. But so these are shape functions. Okay, but the shape functions, of course, all of you know, depends on how many variables that you use. Okay, now the shape functions, if they have to be the same, then the number of variables for u, p, and epsilon v have to be the same. But if they are going to be different, then the shape functions have to be different. So they are going to be different due to certain very important conditions that we require. Okay, so we write them separately. So we write them as Nu, Np, and Nv separately. Or in other words, it is not necessary that all of them are the same. What does it mean? It simply means that if I have an element or a triangular element, whatever it is, and at the nodes I am going to keep the degrees of freedom for displacement. It is not necessary that at the same node I will keep for P, and at the same node I will keep for epsilon V as well. Okay. So they can be at different places, okay, maybe at the centroid only.
Generally, we take shape function same because that's what the same function.
No, you wouldn't have studied these three things separately. It is you use. Please note the difference. You will use the same shape function for all u's. We are not touching that. Whether you are going to interpolate u1, u2, it does not matter. There you will use exactly the same shape functions. We are not talking about that. We are talking about a situation where I have pressure as well as epsilon V to be also interpolated. They are going to be different. They can be different. Okay. Again, as I told you, this is due to certain conditions which I require, and we will call that later as LBB condition and so on. Let's not get into a lot more mathematics at this stage. Let us just look at the end result. Is that clear? Okay. So we will now make Np is equal to just Nv alone, okay, and leave N as it is. So any confusion?
The number will be same. So number of shape functions will be same.
No. Number of shape functions Nu is what I am keeping for displacements.
No, in case we have 5 nodes, so we'll have 5 NUs, and same for the 5 NPs and 5.
No, N's depend upon, of course, use, number of degrees of freedom. Okay. So whether the whole question I'm repeating is whether I have the same degrees of freedom for U, P, and epsilon V. I can have P to be constant in one element. In other words, N can be 1. Epsilon V can be 1, which means that I'm keeping this to be a constant. I'm going to evaluate it such that, okay, Np is equal to, I have to have a single value. Is that clear? That's what we mean. So this is the most confusing step. Okay, we are also putting down a condition that Nv is equal to Np. Right.
What that epsilon V means physically?
1 plus 2 2. 1 plus 2 2 plus 3 3 is always there, depending upon whether you have 3 3 is equal to 0 or 3 3 is there and so on. See, epsilon V does not change. Okay, 1 1 plus 2 2 plus 3 3.
But volumetric strain won't be there in 2-dimensional case.
Of course, it will have, depending upon whether the incompressibility is equal to 0 or not. So epsilon 1, once you have, for an elastic case, you have epsilon 1 1 and epsilon 2 2, you will have a volumetric strain. Of course, you will have. Right? Fine. Now what do we do? Go back to and look at, remember what we did. I have to write down all the variations in terms of N's, that is, in other words, U and epsilon V and epsilon delta epsilon P. So in other words, delta U is equal to, how do I write that? Nu into delta U hat. Please write that down. Delta P Np delta P hat, and delta epsilon V is equal to Nv into delta epsilon V hat. Now, what is my next step? Remember my previous steps. I calculated what is called as B. Okay. Now I have not done that yet. So what is the B that I will get, or what is the relationship between strain and displacement? Remember, I had already written down epsilon. Okay. We had epsilon, we had two terms, right? We just now wrote that. epsilon is equal to, what is it that we wrote? ID into SU, okay, plus 1/3 m epsilon v. So in terms of the discretized quantities, how will this appear? How will this appear? First term will be ID into instead of SU, this will become BU hat, same fashion as you write down the B matrix, plus the second term we had as 1/3 m epsilon v. So what will that become now? NV epsilon v hat. So 1/3 m NV epsilon v hat. See the procedure, please note this procedure is the same. Follow this step by step. Keep in mind what you did in the last class. So what is delta epsilon? So what am I doing? What I am doing is very simple. I am looking at where all I have to substitute things there. I am going to keep writing them in that fashion, then go back and substitute. So delta epsilon is, of course, I can write that as, so the same thing, I'll just change it. Delta epsilon here and delta u hat and delta epsilon p hat. So what is now sigma? Remember what we did for sigma, what do? Just substitute now in terms of my discretized quantity. So sigma has again two things. What are the two things, or what are the two terms? ID into plus m into p. Now what will happen to p? NP p hat. M NP p hat. So having known all this, okay, substitute these things into my first equation. I'm going to get, obviously I'm going to get three equations. I'm going to get three equations. Substitute this, I'll give you 2 minutes, please look at this and this, substitute it and let us see how what you get. Okay, please look at this equation. Of course, you should have written these things in your notebook. So these equations, this equations, substitute it here. Okay. Let's see what you get. Of course, delta U transpose, you have to delta U hat N transpose. Okay. Note that this is the inertia term. If you are doing dynamics, this term will be there, U double dot term. Okay. If you are not doing dynamics, you can, the term is out. Right. So please look at these two terms and write that down. Let me write this ultimate result. I am not going to say what this is. Of course, all of them are matrices, is equal to F. Let me see, you come up with an equation for, say, P and M. It's very simple, there's nothing there. P is nothing but, look at that equation, there's no change. P is nothing but B transpose sigma, no more than that, right? And M is, so P is equal to, from where do I get? No, this I get from P, I get from here, delta epsilon transpose. So delta epsilon transpose is delta U hat transpose, delta U hat transpose will go out. So this term, I can write this down as delta U hat transpose integral B transpose sigma d omega, right? So P remains the same, B transpose sigma d omega. My M will remain the same as you have it in a dynamic case. What is that? Rho, substitute it here. Of course, rho is scalar quantity. So N transpose, this will become, this will go out, delta U hat transpose, N transpose, u double dot you have to substitute. So this will become n u hat double dot. Right? So m is now, that's the quantity. That's the quantity. M is rho n transpose n d omega, your regular m, nothing has happened to it, right, is equal to f. F consists of these two terms. This will become n transpose b d omega, n transpose t, okay, d gamma will be the two terms for the external forces F. So the first equation is the same, there is no change in it. Now I'm going to leave that second thing for a minute and let us see what you get out of the second equation. Now, okay, is this clear?
So delta U hat transpose is also there in the M.
Yeah, delta U at transpose will go off, okay, because obviously you know that from your earlier class, then because it's valid for every delta U at transpose, so that will go off, so it will not be there. So let us now look at the second equation. Write this down for the second equation. Let me write this in Zincuvic's terminology as PP, the final equation, minus C P hat is equal to 0. See, we are writing these things at the element level, understand that. So now what is PP? Okay, and write that down, as well as the third equation, that's the first equation we know, second equation, and third equation is written as minus C transpose epsilon V hat minus E U hat is equal to 0. Now I'll give you 2 minutes, let me see how many of you come up with what is PP. What is the procedure? It's very simple. In order to get PP, I substitute in the same fashion as I did in the first equation. I substitute all these discretized forms into this equation and rewrite this first equation. Is that clear? Okay. Let's see what is PP now. So 1/3 term will be there, very simple, one third term will be there. So this will be delta epsilon V transpose. So here you will get NV transpose. So from here, okay, if you want to keep this here, so you will get in delta epsilon V, you will have NV rather, then I think we should have written that as n delta epsilon V transpose, so that you can take that out. So n transpose 1/3 will be there, of course, you can write that out, n transpose, then m transpose, that will be there. For sigma hat, what do? You can keep that as it is. Yeah, substitute it. And V, of course, d omega. Yes, this may be a worrying term. We will see how we can eliminate that. So that is the PP term. Obviously, I am just substituting it straight away. Okay, in a proper matrix notation, this should have been transposed, so that's why you get that. Then only you can multiply both. Right? Then how does the second term come up? How does the second term come up? What are the terms that will be there? That is C term. Is this clear? That gives me PP. Yes. So NV transpose, yeah, this will be there. So this fellow will go out. So NV transpose, for P I am going to substitute for NP. So integral NV transpose NP d omega. That's all. Right? So this will now become NP p hat. Okay? So C now will become integral NV transpose NP d omega.
What is it? Something after C.
P hat. P hat, how did P hat come? Because P is equal to NP P hat. So that should come there. Right? Okay. Now, third equation. Having done all this, to look at the third equation and substitute. Third equation is slightly more involved. Okay. And let me write, I think I've written down that here. So your whole job is now to find out what is C transpose and E. Okay, slightly more involved, especially E. Okay, you have to define to me what is that term E. It is not that mathematically very difficult. One or two step of algebraic manipulation will give you what is E. Okay, but the procedure is direct. Substitute this back into that equation and determine. Right? Okay. So that's going to take a few minutes. So we'll stop here. Please try this out. Okay, we will carry on with the third equation in the next class. Any questions? We'll stop here and continue in the next class.